Hello developers, let's start developing. I am Veko and today we're talking on the 16th day of the 2024 Advent of Code. So we're doing the Reindeer Olympics this time, which means that we need to find a path to a maze. Okay, we need to get from the start to the end, so first things first, we're gonna need to do some parsing. So our input will be once more a cell, a matrix of cells. So what is a cell? A cell can be a hashtag, which is a wall, or it can be empty, which is a dot, or it can be the starting position, which is an empty starting position, or it can be an ending position, which is an empty once more, but it is our target. So in order to get the data, of course, we're going to get the lines and just map them. Each line, we're just going to split it on line dot split on every, not lines line, the single line, we need to split it on every character, and that's our matrix or maze, as we can call it. And then we return the maze. And if here we say that we're not going to use a string array as an input, but as a cell matrix, I think that we would get an error here because this doesn't return a cell matrix, this returns a string matrix. So we're just going to pretend that you're a cell matrix because that is what you actually are. Of course, let's turn off part 2 for now. Most likely that will be in another video. And let's just print matrix of the input of our initial maze so that we can see that we are parsing the input correctly. This is what we have in our memory. And it is what we wanted to have. So now let's look at what we want to do with the maze. So we can move forward. Starts and start out facing east. East is that way. So we're facing east. And we have two possible moves we can do. Three, kind of. So we can go straight in the direction we're facing. That costs 1 point. Or we can turn clockwise. We can turn clockwise, which costs 1000 points, or we can turn counterclockwise, which again costs 1000 points. And we need to get basically to the place, to the end. So 1 turn, 2 turns, 3 turns, 4 turns, 5 turns, 6 turns, 7 turns, and we're getting there. And we have a second example that we can also do. Yeah. And it costs a certain amount of things. So the thing is that we kind of have a graph here with neighbors and everything. And we need to do the minimal path through the graph, which is basically Dijkstra. But note that I have burned myself last year on the topic, on the task when we had something that moved at most 3 points in the same direction. So the directions are kind of important, and I totally feel that way. So what I will do, I will somehow make this into a specific graph, but graph that has kind of unusual neighbors. So I will say that this point is not the point, it does not consist of the coordinates only, but a point consists of, or a node, since we're talking about graphs, will consist of the x and the y, not the distance. Actually, we might need to have that because of Dijkstra, but that's for later. And it's also the way that it's facing. And that will be northeast, south, or west. And to that node, it will have three neighbors. The first neighbor will be the same x and y coordinate, only facing, if it's facing north, facing east. The second neighbor will be same numbers, facing west. And the third number will be have the same facing and the exact same x, only y will be y minus 1. So those are the neighbors that it gets. So what I will want to do is to actually make a list of all the nodes in the map. And for that I can use simple flat fill. And yeah, I can have the price here as well, which will be a number. And since we're trying to minimize the price by default, it will be the maximum number. So let's have it like that. Let's implement a find neighbors method. So we have our node and we have our maze, and we need to find all its neighbors. And this might be kind of weird. So this is the weird part. The neighbors of the node. Yeah, let's have it as an empty array of cells, of nodes. Yeah, this will return a node array, of course. So if we can always turn, so that's not a problem. Of course, if we turn into a wall, then we couldn't move next time, but that's a problem for later. So we can always turn. We can turn clockwise. Yes, those are the directions. Directions are actually once off. Yeah, we're gonna. No, we don't want to do that, but I will hard code them. So if we're facing north and we turn clockwise, we're gonna face east. And this goes in a circle, so if we're facing east, we're gonna go south. If we're going south, we're gonna turn west. And with the other kind, with the other counterclockwise directions are totally in the different way, but I don't think that we're correct. So if we're facing north, we're gonna face west. If we're facing east, we're gonna face, oh yeah, this got it wrong. If we're facing east, we're gonna go north. If we're facing south, we're gonna face east, south, east. And then if we're facing west, we're gonna face south. Yes, those are the counter directions. So direction index will be directions index of the way we are facing. So let's get this here because we need it anyway. So neighbors dot push, we're gonna add the neighbor when we turn clockwise. So that has the same x, the same y, the facing is in that way, and directions, right now this is an array of string. We will take these and make them into a type so they don't complain. This is facing, yeah. I can call it, so this is a facing array. And so it's clock directions, so is this, and now we don't have a problem. And the price will be bigger by 1,000. Turning counterclockwise, we have these counter directions, and now we can move forward, and we will have yeah, this is actually a very nice code. The dx, we're calculating how much we're going to move in the x direction, that is that one. So if we're facing east, x is going to increase. If we're facing west, x is going to go down. And dy will be the exact same thing. If we're facing south, x is going to go y is going to go up, facing north, y is going to go down, otherwise it stays the same. So dx and dy is the amount of moving we will do in that direction. So now we can just say, yeah, we can have nx and ny. We don't really have that, but we can say if is not a wall, yeah, this is great. So if it's a wall, that's not a neighbor. If it's not a wall, then it is a neighbor. And we'll move dx and dy in the direction we're moving. We're keeping the same facing, and the price of the path so far is that +1. So we know how much we will need to go to get to a certain place. So we can find the neighbors or of each of that. So we will also need to find the start. Yeah, this is basically a nested loop. We find the row that includes the S, and then we find within that row, we count the index of S, we return those X and Y, so we can start with. Start is find start. The start node, we're facing east, and the price to get to the start node facing east is exactly 0. What we're gonna do, actually I'm gonna copy our input and call it maze, is gonna be input.map row slice, and that is a copy, because now when we found the start, I don't care about it anymore. So we can say maze of start y start x is dot. Let's have also find this end. Yep, exactly that. Let's find the end, and we're gonna make that into a dot as well. So we can say while const, and actually we're gonna have something else for the maze. each dot of the maze can have an extra number, which is the maximum price, the minimum price that we use to get there, which will tell us whether there is a better way to get to this thing or not. So we're going to take the row and we're going to map each cell. No. We're going to map each cell into an object that has a cell value visited. We don't care whether it's visited or not. We can visit it multiple times, but we will have it as price. And that price will be number dot max safe integer, let's say. We can change this. This is the cell value. So the cell will be empty and the price will be 0 because it's the start. So we don't need the start node, we need the node. And we can be doing this. Yeah, we can have it as the start node. So now we're gonna do a simple loop. While we do, this is basically Dijkstra. And this thing knows how to do that. So we have a queue. While our queue has items, we're gonna take the first item, and that is our current thing. For the current thing, find all the neighbors for each of the neighbors. And I don't like for each, I like for of. I hate impure functions, even though everything is the same, only the format is different. So if our neighbor is the end point, then we found it. And the price we found it is that. Otherwise, what we do? We see what is the price of our neighbor. And note that our neighbor will likely be the exact same cell, except in a different direction. Oh, we messed up. The price is not this, it's not a number. So the price is this. If we are facing north is that, if we are facing east is that. Oh, and the start has, basically we can use the prices. If we're facing east is that much, and if you're facing west is basically that much, because in order to turn west we would have to turn twice. Yeah. So this, we have 3 dimensions. We have x, y, and facing. So if the maze of that neighbor, price of that neighbor dot facing is bigger than, so this is the active price for that point in that direction. It's bigger than the price of the neighbor. Note that the neighbor is already facing. Then we will update this here and push it. And to be honest, I will put this as, yeah, I want to do this way. I don't want to do anything because otherwise it might not get queued. And it should be enough, since we're already returning here. So the idea is that each dot will find its neighbors and then queue those neighbors. If we find a cheaper way to get to that neighbor, we queue that neighbor. Otherwise, we don't. This is not ideal because we will reprocess a lot of stuff. We might want to do some reordering of the queue to get to an A star so it's better and faster and things like that. But in general, this feels like it could work. Let's see if we get some value. It says 10,028. I don't think that was correct. The good news is this thing finished. So we have, a, it took a different path. So let's somehow debug this. So after it's done, maybe we want to print the maze. This won't print anything. This will print basically. Oh, oh, the actual return is here. We can replace this with throw. Let's run this. This will just give us the exact maze that we have. I will tell it to actually print it in a bit of a different way. This is the row header, we don't need that. To print the row cell, and then yeah, why not? Whether this looks like something, we might get something very, very bad. No, we will need a better printing function, definitely. So let's make one. So this is quite okay. If it's a dot, no, not cell. We need this thing. Yeah. For now, I will say any. If it's a dot, then I don't like any. Because the price of the ball will always be that, but we can actually get mat.min of cell.price. Yeah, that's enough. So cell to print cell. Where is the problem? Return, oh, return. Default, return, space, space, space. It's enough. That should never happen, but it should work. Type number or that is not assignable to fixed. Okay, we can live with that. It's bitching because it doesn't have a string. So we should get something that looks weird. But it kind of makes sense. I will add a few more spaces so that it looks better. Three, four, five. Let's pad it to 6. We should never see it, so it doesn't really matter. Yeah, we can see it better now. 0. Let's experiment a bit more because I have a feeling that we can have a really nice visualization of this. Oh, and I think I already know what the problem is. Yep, 10,028. So let's compare this to what the preferred path is. So we started from here. We actually found the shortest path and not the cheapest path. So if we go this way, this has price 1, this has price 2, price 1001, 1003, and so on and so forth. And one property of Dijkstra is that it's always going to find the shortest and the cheapest way. But now we have a specific scenario because we have kind of 4 different ending nodes in 4 different directions that the first node we found might not be the last one, might not be the best one. So we found this one. So for example, you can see that to get to this position you can get from 2006 over here with a price of 3007 or from here with a price of 3005. So we're always going to take the cheaper version. Same thing here. So that is correct. And what we did was we, I guess, went this way, then went that way. And instead of using this route, we took this route, which has more turns, but it's shorter. Yeah. Because this route goes all the way down and all the way up, and we found this route which is shorter and more direct. It only has more turns and it's that long. So the point that we finished, these things were still left in the queue. So we might want to actually process our queue all the way. So instead of returning, we will just say if this is better than the best price, then set the best price to that, and at the very end we're just gonna return the best price. Because we might have a route that is longer but cheaper. It's not that we found a route, we need to find the best route. So which means we keep running until we run out of places to go. So this one is, we found an end We found that first. There were a few routes that were even more expensive, but then we found this one and we said that the best one is 7036, which is the correct one. So we have a second example as well. Let's try that one. And let's see what it gives us. It found 4040, 15,040, but the best path is 1148, and the best path we found is 1148. Finding all the paths might be a bit problematic, so I have no idea whether this thing for the huge input will actually work, but in general it should. We might want to do some optimization that we're not finding, that each new path we found is kind of cheaper than the previous one, that we're not able to find a path which is more expensive. But let's see. Oh, this runs surprisingly fast. So we say that this is the cheapest way that we can run through this maze. Let's see if that is the correct answer, and yes it is. We got lucky. Let's just take a glimpse at the second part and then we're done, because usually these things are very, very hard on the second one. The best spot to sit. Oh, we wanted actually to find the best spot to sit is a good place. Non-wall tile, places to sit along the edges of the tile would be the whether the tile is on the best path. So we need to sit on the best path. Oh, this is complicated. So note that we found the price of the best path. It doesn't necessarily mean that that's the only best path, because, for example, look at this part here, or better here. So we can go this way, this way, this way, or we can go this way, this way, this way, and those things are identical. Let's go back to our thingy. So we can get here with the price of 2007, whether we're going from here or from here. This has the minimum price of 2006, because to get here it's cheaper to get like this. But to get to this thing, the minimum price is always 3007. So it doesn't really matter. So we need to find all the best paths, which, to be honest, at the moment I don't know how to do. I think we have a nice structure that will enable us to add a bit of data and get to the best path, but I'm not sure. Anyway, we got a win, we got a star, so I'm gonna take that and run with it. And as for you, click like, subscribe, and all those things. Don't click the bad button, and keep developing.